Hello and welcome back, everyone. Today we're going over 9.6, which has two more tests for us, the ratio and root test. So we'll start with theorem 9.17. It tells us that a series adding up all a sub n converges absolutely if limit as n goes to infinity of a sub n plus 1 over a sub n inside the absolute value is less than 1. Here we're going to assume non-zero terms. We'll assume that it diverges if our limit is either greater than 1 or equal to infinity. Really, that's kind of... infinity is definitely greater than 1. And the only case then we haven't looked at, if it's equal to 1, the test is inconclusive. All right, so we'll take a look at a couple examples here. We'll go from n equals 0 to infinity of n factorial over 7 to the n. And see if this thing converges or diverges based on the ratio test. So we'll take the limit as n goes to infinity of n plus 1 factorial over 7 to the n plus 1 divided by, and instead of putting it over, I'm just going to go ahead and put the divided by next to it. So divided by n factorial over 7 to the n. So this is the limit as n goes to infinity of n plus 1 factorial. I'll go ahead and turn that into n plus 1 by n factorial. Similarly, 7 to the n plus 1 power, I'll turn into 7 to the n times 7 to the first, multiplying with the same base. Your shortcut is to add those exponents up. I'm going to flip the other fraction, so 7 to the n upstairs, n factorial downstairs, and you'll see why we did those little bits of separating. So 7 to the n or 7 to the n is worth 1. N factorial over n factorial is 1. And then we let n go to infinity. Well, here we have infinity plus 1 over 7, which is infinity. So this tells me the series diverges. Okay, another couple problems with the ratio test. Then we'll hit our friend the root test. Make sure I'm centered nicely here. There we go. So this next one, we'll start at 1, go to infinity. 5 to the n plus 1 n squared over 8 to the n power. So again, one that this one looks a little bit messier. With the root test though, not as bad. Just let n go to infinity and do the ratio of the n plus first term to the nth term. So n plus 1 turns into n plus 2 on the exponent for the 5. N squared is now n plus 1 quantity squared, and downstairs 8 to the n plus 1 power. So we're dividing by 5 to the n plus 1, n squared, over 8 to the n. So a to the a sub n plus 1 divided by a sub n. Take that limit as n goes to infinity. Okay, so a little bit of work on this. The limit as n goes to infinity. So 5 to the n plus 2, I'll turn that into 5 to the n times 5 squared. Again, multiplying with the same base, we're adding those exponents. Then we have n plus 1 squared over 8 to the n times 8. And multiply by the reciprocal of the other guy. Okay, so we do get a little bit of work done here. 5 to the n, 5 to the n will drop. 8 to the n, 8 to the n will drop. 5 squared over 5 is 5 to the first upstairs. 8 to the first downstairs. So as n goes to infinity, we have an n squared over an n squared. Those will go to a 1. So we have 5 ace times 1, or just 5 ace. This is less than 1. If it's less than 1, we know the series converges. So it doesn't guarantee it's easy to find what it converges to. It just guarantees that, yes, the series will converge to some value. Doesn't necessarily mean it's an easy fix. All right, so next up, sum from 1 to infinity, negative 1 to the n by n plus 1, all over root n. And again, we're going to try the ratio test. Ratio test, we take the limit as n goes to infinity, n plus first, so negative 1 to the n plus 1, times n plus 1 is n plus 2, and downstairs root n plus 1. And then we're dividing by the a sub nth term, so negative 1 to the n plus 1 over root n. So again, we're still letting n go to infinity. So we have negative 1 to the n times negative 1 by n plus 2 over n plus 1 to the half times n to the half up top, negative 1 to the n by n plus 1 downstairs. After that, again, we're back to doing a little bit of cleanup. Negative 1 to the n, negative 1 to the n. Looking at what we have left, not a whole lot of canceling that we can do there. We have the negative 1 by itself, but we're in absolute values. We can just kind of cut that loose. N plus 2 over n plus 1 by the square root of n over n plus 1. So we regrouped our square roots and non-square root terms. As n goes to infinity, this guy goes to a 1, this guy goes to a 1. 1 root 1 is still just 1. This tells me the test is inconclusive. So we would have to perform a different test. If we do the alternating series test on this guy, take the limit as n goes to infinity of our n plus 1 over n to the half That's the limit then as n goes to infinity. We can break it up. N to the first over n to the half is n to the half, and then plus n to the negative 1/2. So this goes, first term goes to infinity, second term goes to 0. Since the limit does not go to 0 by the alternating series test, we know this diverges. So the ratio test, not always conclusive. You will occasionally have to find another way to finish the problem out. Alright, so next up, we take a look at our friend the root test. So this is Theorem 9.18. Again, we have some series. And our series converges absolutely if take the limit as usual, n goes to infinity. The nth root of absolute value of our a sub nth term is less than 1. We know it diverges if that limit is greater than 1 or goes to infinity. And much like the ratio test, if it's equal to 1, test is inconclusive. So inconclusive, we would just break out another test, try something else. Alright, so some examples of this at work. Go from 1 to infinity, e to the 7n over n to the n. So the root test, I take the limit as n goes to infinity of the nth root of absolute value of our nth term, so e to the 7n over n to the n. So this is then the limit as n approaches infinity. The absolute value of e to the 7n over n to the n over n power. And n over n, of course, is a nice, neat, pretty 1. So now we have the limit as n approaches infinity, absolute value of e to the 7th over n. Now as n goes to infinity, this of course then would approach 0. E to the 7th is a constant over a bigger and bigger denominator. We get closer and closer to 0. Since this is less than 1, the test concludes that this series converges absolutely. Alright, so our general strategy, now that we have quite a bit of tests for divergence and convergence under our belts. As the limit as n goes to infinity of our a sub nth not equal 0. So if we're not heading to 0, on our terms, we know that the series will diverge. And we look for some of the special types of series that we've seen, geometric. And we saw how to find the sum of a geometric series, p-series. Pretty quick, straightforward test for that guy. Telescoping series. We found how to actually find the exact value of the infinite sum for a telescoping series. And of course our friend the alternating series. So if it's not one of our specialties, then we can do the integral test. Root test or ratio test. Or we can do the comparison. So that's kind of a general outline if it's not saying on the problem exactly what strategy they want you to take. That's kind of a rundown of the order that you would take a look at it. Alright, so in 9.6, I would try 1 and 2, then 13 to 67 odd. I did want to leave also a hint on number 29 to examine n plus 1 over n plus 2 to the nth separately. And on that one, you will end up seeing our friend L'Hopital show up. Okay, if you have any questions, please come see me. Otherwise, I'll see you for the next video. Stay safe out there.